So today I want to start off with looking at some actual data. At the end of class on Tuesday, we did a very small data set on calculator, Excel, Mathematica, and R. So today we want to look at a bigger data set that I sent you about relating treasury bill returns to inflation rates in a spreadsheet here. And mostly we are going to focus on a spreadsheet because that'll be simplest here to start off with when we've got a bigger data set. Help us see the big picture of regression is the main goal here. So we're going to go through all sort of the main things that people go through with regression. As we get near the end, well, we'll also talk about the theoretical regression model, which you find in the reading in the first couple sections of chapter 11, which you should have done. I know it was not easy reading, but you really should work at it. So we'll go over that regression model. And then as we have time at the end, we'll see if we can import the spreadsheet data into both Mathematica and R. I did it before class. I had success with Mathematica. I did not have success with R because R was telling me that I had some package that I had to load. Then I tried to load it and it still didn't work. So I'm not exactly sure what's wrong with my version of R. At least you could try it with yours and see if you get yours to work or not. Hopefully we'll have time for that. So yeah, data here from 1958 through 2013. So not recent years, not the last 9 years of treasury bill returns, which are essentially government debt. The government sells treasury bills and they also sell other kinds of debt. It's a bond. You are buying treasury bills when you invest in treasury bills, and then you get a return. It's part of the government's debt. The national debt comes from those kinds of things. So there's a certain interest rate of return here that you see in these different years. In more recent years, as you know, interest rates have been lowered. Now with inflation going up, perhaps interest rates will go back up. That would be interesting for us to see. I won't do it today, but hopefully next week we can look at more recent data and see if the model that we find with this older data matches what's happened more recently. That would be an example of a good use of regression to sort of test and see if the model is staying pretty consistent or not, or if it needs to be updated. We also see inflation rates. Inflation was real bad in the mid-70s through the early 80s, as it's getting bad right now. Will it get up to the worst year, which was evidently 1979 of a 13.2% interest rate? I don't know. I guess the news reports I've heard is more like 7 to 10%, but we shall see. Okay. So first thing we're going to want to do if we're going to do a regression is think about which of these variables we would want to predict from the other variable. Would it make more sense to try to predict treasury bill return if you know inflation? Or would it make more sense to try to predict inflation if you know treasury bill return? In theory, you might say you could go either way. However, in practice, if you're thinking about real life applications here, it makes the most sense to say, I'm an investor. I'm wondering if I should invest in treasury bills in these coming years. I have guesses about what I think inflation is going to do. So maybe I should try to use these data to predict treasury bill return when I know inflation. Does that make sense? From the point of view of an investor. So because of that, that means these columns, as they are in the wrong order. You want to predict Y when you know X. Here we want to predict treasury bill return when we know the inflation. In other words, the inflation column should be the X column, and the treasury bill return should be the Y column. So for the sake of simplicity, I'm going to switch the columns, and I'm going to do it in Google Sheets. Again, because when you have Excel on a Mac, the tools that you can use are not quite as good as if you have Excel on a PC. In particular, again, I'm thinking of the XLMiner analysis tool pack. So I'm just first going to go ahead and copy the year. We're not going to use the year today. We could use the year in other days next week, but today we're not going to. Let me pick the inflation column next. That'll be my X variable, my explanatory variable. Just copying and pasting. And then my response variable, treasury bill return, is going to be Y. I want to put that in the next column. And again, like I showed you on Tuesday at the end of class, the quickest way to get the regression line is to go ahead and make a graph and insert the regression line and the squared correlation into your graph. So I'm highlighting all the data. I'm going to insert chart. Okay, it's not picking a scatter plot. Didn't it pick a scatter plot by default the last time? I thought it did. You don't want that particular chart. It is maybe kind of pretty, but that's not what we want. We want a scatter plot, scatter chart, scattergram. Those are all different words for the same thing. I think I usually say scatter plot. There we go. Let's customize it. Go to series, add in the trend line, which is the regression line, and show R squared. R squared is about 0.481, close to 0.5. That's the squared correlation. That means the actual correlation, if you think about it, would be close to 0.7. And it is a positive correlation because you have an upward trend. The trend line here, the regression line, has a positive slope. .481 is what that says, if you can't quite see it. And for a label, let's use equation. There we go. T-bill return is the Y. T-bill is effectively Y equals 0.703x plus 2.3. That R squared is a separate thing. I'm going to go ahead and write that down here. So here we are. What are the coefficients again? The slope is 0.703 and the intercept's 2.03 or 2.3. You could call this a sample regression line. We are going to be talking inferential statistics here. So I'm going to call this a sample regression line rather than a population regression line. And if you did the reading in chapter 11, you know what I'm talking about. To predict T-bill return when the inflation rate, which I'll capitalize as well here, the first letters at least, inflation rate is known. So the T-bill return, maybe I should capitalize return. The T-bill return as an interest rate, that's your response variable. The idea is that it responds to the inflation rate, which is a generally true thing, by the way. Think about what's going on right now. So this is the response variable. This is the explanatory variable. Think about what's going on here in April of 2022, right? For the past year or so, inflation has got a lot higher. Most people think of that in terms of prices going up, but economists think of it more in terms of the value of a dollar going down. So since the value of a dollar is going down, it takes more dollars to buy the same thing. What is the Federal Reserve doing? If you've watched the news or read some articles or anything, you should know that it's going to raise interest rates if it hasn't done so already, above the prime rate. Other interest rates respond to that. They also respond to inflation because of supply and demand. When the inflation rate is high, investors are going to demand a higher return to buy your investment, whether it's a bond or stocks or whatever. They're going to want higher returns. to make up for the fact that inflation is so high. But there's also the fact that the Treasury raises sort of the prime interest rate, which causes mortgage rates to go up, which causes T-bill returns to go up. T-bills being effectively a bond set the interest rate that they are trying to sell it at ahead of time. They're trying to sell it to investors at a certain interest rate. So it's a natural thing for that to respond to the inflation rate. This is Y, this is X. I'm going to write the regression equation as Y hat, which you could also write maybe as T-bill hat if you want to emphasize what the variable means. T-bill hat. I forgot it. What was it? 0.703x plus 2.3. That's, I'm sure, an approximation. 0.703x plus 2.3. What's the most basic kind of application of this? The most basic kind of application is to plug in a value of X and get a value of Y. Get a predicted T-bill response when you know the inflation rate. By the way, you could also use a more descriptive name for X. You could maybe label that INFL or something. That's not another National Football League, by the way. What's the new one? Is they call it this USFL or CFL? I forget. Or not. USFL. CFL is Canadian Football League. I don't know if you know this, but the USFL, there was a USFL 30 years ago as well. That was in the 80s and they had folded. But now it's back. I don't know if you know the name Herschel Walker, but if you're a Vikings fan, Herschel Walker was infamous. The Vikings traded the house to Dallas for Herschel Walker back in the late 80s. It was a running back. It was a pretty good running back, but he wasn't worth what we traded for him. And yeah, he kind of let us down. But anyway, Herschel Walker was in the USFL, if I recall correctly, right after college in the 80s. And he did really well in the USFL, just not as well in the NFL. All right, sidelight there. So again, most basic use is, okay, let's think about what's going on right now. If X is 7%, if that's the true inflation rate, say for 2022, which it might be low, it could be like 8 or 9 or 10%. What would we predict will be the T-bill returns over the course of the year? Now, T-bills are sold at different times during the year. So when you talk about these numbers, you're talking really about averages. These numbers are given as percentages. I don't convert the 7% to a 0.07. Effectively, the units on the X values and the Y values for that matter are percent, though you don't see a percent sign in there. So I do want to literally plug 7 into this equation, not 0.07. .703 times 7 plus 2.3. Based on past data, we would predict a Treasury bill return of 7.2%. Now, in reality, you got to compare it with reality. I don't think the Treasury bill returns are up that high yet because they've been very, very low, less than 1% recently. They're probably going up. I haven't looked it up. I should. Probably this weekend, I should look it up. But I don't think they're up that high yet. Though maybe you'd argue by the end of the year, they could be closer. Or maybe next year, if the inflation rate stays at about 7, it could be closer. Let's see what happens if we increase X to 8%. You should know what happens. You know about slopes as rates of change, right? something basic we teach in calculus. 0.703 is the slope of the line. It's the rate of change. I've increased X by 1 unit. You could call it 1 percentage point. Don't say 1% because it actually increased by more than 1%. 1 divided by 7, what is that, 14% or something? It actually increased by 14%, but 1 percentage point is the way you say this if it goes from 7% to 8%. So the inflation return, the T-bill return and prediction should go up by about 0.7, should be about 7.9%. Let's see if that happens. Oops, change that 7 to an 8. 0.703 times 8, and then add 2.3. Yep, close to 7.9%. So that's the most basic use of the regression line that people use, is just to make predictions about the Y value when you know X. Are the predictions any good? Short answer is it depends, right? It depends on what's actually going on in real life, including right now. It's probably not so good right now. Again, I'll look it up over the weekend. Is it fitting with these past data? How would you interpret this graphically? Inflation's on the x-axis. We just plugged in x equals 7 and y equals 8. When x equals 7, go up to the line. The predicted T-bill return is the second coordinate of this point, which you can see is close to 7. Plug in 8. T-bill returns up here, which is now close to 8. You could graphically plug in some other number like 2. If the inflation rate was 2%, like it was more last year or the year before, you'd predict T-bill return just graphically here close to 4%. I do want to show you the XLMiner analysis tool pack, but before we do that, let's confirm the regression line is correct using the equations that we derived on Tuesday. This is the inflation X. This is the T-bill return Y. What were the equations that we derived for the slope and intercept on Tuesday? The slope, here's the way I remember. Okay, you can look in your book as well, of course, but it is good, I think, to try to remember. I remember it as a fraction with those SS symbols I showed you on Tuesday. SSXY divided by SSXX. Now, the definition of those symbols is as follows. For SSXX, SS stands for sum of squares. By the way, the book just calls these things, just uses one S. This is in the text. I like using two S's to remind myself, at least in the case of the X's, it's a sum of squares. It's this sum. For the numerator, it's not literally a sum of squares, but you could say it's analogous to squares, except you use both X and Y's. You add up the products Xi minus X bar times Yi minus Y bar. So this will give you the slope of the regression line. However, it's not the usual equation that's used when people use an equation. They usually expand these things out and verify that the numerator turns out to equal this summation, or this expression, the sum I goes from 1 to n of xi times yi minus, it turns out, the sum of the xi's times the sum of the yi's over n. And the denominator ends up equaling the sum of xi squared minus the sum of xi quantity squared over n. That's still not the final form in the book, because what the textbook does, the authors do, is they now multiply the top and the bottom of this by n. It's the yi here, by the way. And if you multiply the top and the bottom by n, you get rid of the fractions within fractions. But when you don't have over n's, you need n's in front. So the book writes the slope formula this way. It gives you the same answer, though technically it's no longer the ratio of SSXY over SSXX, but it gives you the same answer. I multiplied the top and the bottom both by n. Oops, I made a mistake, sorry. All right, let's confirm this gives the right answer. Okay, so the numbers are starting in B2 and C2 here. Let's put the calculations down here. Well, the summations at least. We are going to need to add up the products of the x's with the y's, of the corresponding y's. Add up the squared values of the x's. So if I want to confirm this formula with the spreadsheet, I should make 2 more columns. One with x squared values and one with x times y values. So in cell D2, I'm going to type equals B2 squared and copy and paste that formula down. Actually, I could have done my copying and pasting with 2 columns at once. In cell E2, I'm going to do equals B2 times C2. Each x gets multiplied by the corresponding y. Click and drag that down. All right, let's do the sums of the columns. So equals SUM, B2 through B57. B2 colon B57 will add up the numbers in column B, which are the inflation rates. And I can just click and drag that over to the right to add up the other columns. So this is the sum of the x's. This is the sum of the y's. This is the sum of x squareds. And this is the sum of x times y's. Did you get those numbers? How are we doing? You keeping up with me? If you feel like you're hopelessly behind and catching up, maybe it's better to just focus on what I'm saying. How many numbers are there? What's n? Well, the last data point is in row 57 in the spreadsheet, and the first data point was in row 2. So there's 56 numbers, n is 56. Maybe I should put it below. Or maybe I should, well, okay, yeah, maybe I should put these things above that. All right, now let's do the slope and the intercept. I haven't written down the equation of the intercept. That's okay. Let's just do the slope first. It's n, which is in cell C62. Use parentheses though, because I'm going to divide. N times the sum of the x times y's, which is in cell E59, minus the sum of the x's times the sum of the y's. Is that big enough to see? Probably not. Pulling back here. Yeah. Let me redo that. Okay. Divided by n, C62, times the sum of the x squareds. That's in D59. Minus the sum of the x's, which was in B59 squared. So this should be 0.703. Yes. The intercept, B0, is y bar minus B1 times x bar. Which you could write as one fraction if you wanted to. You could write y bar as the sum of the y's divided by n. And x bar is the sum of the x's divided by n. And then you could combine those fractions to say it's a fraction whose numerator is the sum of the y's minus b1 times the sum of the x's, all divided by n. And if you wanted to, that's a b1. Oh, okay, this is a time symbol there. If you wanted to, you could substitute this formula into there in place of b1, and you could try to simplify it, but it's not necessary. Just use the b1 you already found. Of course, I could find averages. I could find x bar and y bar as well. But the sum of the y's was in C59. Minus B1, which is in D62, times the sum of the x's, which is in B59, divided by n, which is 56 in cell C62. So this should be 2.3. Yep. Let me show you one more way to get the slope. I think it's worth showing you this other way to get the slope. The other way to get the slope is to, well, you really only need the standard deviations of the x's and the y's as well as the correlation. Equals STDEV, don't add a P. We want a sample standard deviation of the x's, go B2 through B59. You could call this S sub x, which is a single S and a single x. It's about 28.3188. Was it 57? Oh, yeah, okay. Yep, thank you. 57. There we go. That makes a lot more sense. S sub x with one S and one X is the standard deviation of the x's. It's about 2.906824, say. S sub y with one S and one Y is the standard deviation of the y's. Copy and paste this over. That's about 2.945625. The correlation R can be found with equals correl 2 R's, 1 L, B2 colon B 57, comma, C2 colon C 57. And if I recall correctly, this was about 0.48. Equals correl 2 R's, 1 L. Yeah. Oh, oh no, excuse me. That's the correlation. The R squared is what's about 0.48. R squared is about 0.48. R squared does have a name. It's called the coefficient of determination. And like I said on Tuesday, it's really a better measure of the strength of the linear relationship than R itself is. They both do measure the strength. If R is close to 1, it's a very strong positive linear relationship. And if R is close to -1, it's a very strong negative linear relationship with a negative slope. Of course, if R is close to plus or minus 1, then R squared will be close to plus 1. But it turns out, for reasons we'll see next week, R squared is a better measure of the strength of the linear relationship. This R squared value is close to 0.5. In other words, you might call this example a prototypical moderately strong correlation or association between these two variables. Prototypical, moderately strong. Not really strong, not really weak. I guess if you say moderately strong, you could also say moderately weak. More typically, people are going to say moderately strong. It's tough to eyeball the correlation very precisely just looking at the scatter plot. If you're just looking at this graph over here, it's a pretty tough skill. It would take a lot of practice to be able to guess that R is close to 0.7 and R squared is close to 0.5 there. I mean, am I good enough to guess that? I probably wouldn't be too far off. But even, yeah, I'm sure if somebody told me to guess R squared, I would not necessarily guess 0.48. I might guess somewhere between 0.4 and 0.6. But I probably would not guess, 0.48 to do 2 decimal places of accuracy. So what do we get for R? We got 0.6938. I forgot to write that down. Here's another formula for the slope. To tell you the truth, I forget if this formula is in our textbook or not. It's the correlation times the ratio of the standard deviations, SY divided by SX. Try it. So the ratio of the standard deviations, which in this case is pretty close to 1, doesn't always happen. 2.945625 divided by 2.906824. Multiply times the correlation, 0.693814. And there's our friend, 0.703. That's the slope. So that is an alternative formula for the slope that I think is worth knowing. For one thing, if you've got the correlation, you've got the standard deviations, it's quicker to use. For another thing, it does help you interpret the slope as a rate of change in the following way. We know that the change in Y along the regression line itself is exactly the slope times the change in X along the regression line itself. right? That's the meaning of rate of change, the slope as a rate of change. The change in y is the slope times the change in x, because the slope is rise over n, change in y divided by change in x. If I replace the slope with this thing, I could rewrite this equation as r times sy over sx times delta x. And if I think of changing x by certain fractions of standard deviations, like 1 standard deviation, for example, this estimate of the change in y along the regression line, well, it's an exact thing along the regression line itself, and therefore it's an estimate of the change in y for the data. If delta x equals s sub x can be simplified to just r times s sub y, because the s sub x's will cancel. And I picked delta x to be 1 standard deviation of the x's. I imagine letting x increase by 1 of its standard deviations. I could have picked something different. I could have picked half a standard deviation, 0.5 sx. And if I had done that, then this would have an extra 0.5 in it. The sx's would still cancel. If I do a 1/10 of a standard deviation, 0.1 sx, the sx's still cancel. I'm left with this with an extra 0.1 factor as well. And what this is telling you is actually something significant and worth knowing, is that along the regression line, y changes more slowly than x does if you use units of standard deviations, because r is going to typically be less than 1. So y changes by fewer of its standard deviations than x does along the regression line. We'll try to reason out why that makes sense graphically at some point. I'm not sure if we'll do it today, but these are things worth knowing. Okay, so yes, write those down if you. I hope you wrote them down. Okay, let's now move on to thinking about inference. And let's go ahead and get that XLMiner analysis toolpack output now. If you're in Google Sheets and you don't have XLMiner analysis toolpack, you can search for it by getting add-ons. XLMiner analysis toolpack. There you go. And you can load it. Okay. Doesn't get the greatest reviews, but it is popular. It seems to work fine for regression. I don't have any complaints. I don't use it for much beyond regression myself. So load that, install it. And then when you go back to the tools menu, you should see, or the extensions menu, you should see it there. So we'll go ahead and start that now. And we'll go down to linear regression. Okay, write this down. Once you've opened that up, the very first thing I personally always do, and I would suggest that you do, is I click the labels box. That's the first thing I do by default. What does that mean? That means when you do the input X, Y range and the Y range, the labels, in other words, the inflation and the T-bill, are going to be part of those ranges and will help you interpret your output because they'll be labeled correctly in your output. The Y range goes C1, what was it, through 57? C1 through C57, you can click there and highlight that column. You could also just type C1 through C57. And the X range is B1 through B57. Go down further. The confidence level for certain confidence intervals is by default set to 95%. And yes, that's fine to leave it that way. What goes in output range is a cell reference that is going to be in the upper left corner of the output. Where should that be? Well, maybe anywhere where it's not going to interfere with the data in the graphs. So maybe I want to go down to cell G22 looks good. I'm going to type G22 in there. It's going to be the upper left corner of the output. Let's go ahead and make check the boxes that say residuals and residual plots. Let's leave the rest alone for the moment. Click OK. Does a little work and gives you some output. What do we see? First, there's regression statistics. Multiple R is effectively R, correlation. Why are they calling it multiple R? Because as we'll see in chapter 12, when you do multiple regression, it's not the same as the correlation. The correlation is always going to be for us between two variables. But with multiple regression, there will be an analog of the correlation relating the one response variable to many explanatory variables. Multiple regression, in the most common application, is about trying to predict Y when you know the values of many explanatory variables. Maybe in the abstract, we call them x1, x2, x3, etc. through xn. There's R squared, 0.48. What's this? Adjusted R squared. Okay, we haven't talked about that yet. Don't worry about it. Here's n. That's the number of observations. What's this thing? It's labeled standard error. If you did the reading, you saw a formula for not the standard error, but it's square. Right here. S squared is SSE, our old friend from Tuesday, sum of squares of errors, where errors means residuals, divided by n minus 2, not n minus 1 or n. That's got to be related to S squared being some sort of unbiased estimator for some parameter. I haven't said what that parameter is yet, though. Pretty soon. There's something called a ANOVA output. Let's skip that for the moment. And then there's this stuff right here. Notice this number here is the slope and this number is the intercept. Hey, intercept is labeled with intercept. Why is this one not labeled with slope? Because if you got more than one explanatory variable, that's like you'd have lots of slopes. Lots of rates of change in different directions. If you're trying to imagine multivariable calculus, higher dimensions. So, I mean, it could label them if you've got, say, 5 different explanatory variables. It could label them slope 1, slope 2, slope 3, slope 4, and slope 5. But it's better, more helpful, to label them with the variable they go next to, in this case, the inflation rate. You know this is the rate of change of the T-bill return with respect to inflation. What's the rest of this about? The rest of this is about doing inference. saying our sample regression line is just an estimate of some theoretical population regression that we don't know. And because we're using a random sample, we shouldn't expect the slope and intercept here to be exactly right for the population. You hope they're close if you're doing random sampling and if the sample size is large enough. But just because of the random sample you happen to pick, it's not really so random in this example because we're just looking at T-bill return and inflation data for all years between, what was it, 1950 something and 2013. So that's not really a random sample in the usual sense of the word. In the usual sense of the word, at least. Is there a new way we could think of it as a random sample? Perhaps. If you imagine the population perhaps being described by a theoretical model is one way to imagine it as a random sample, perhaps. But even then, we might be running into trouble because we are talking about consecutive years where, you know, inflation rates and T-bill returns are not going to, they're not going to bounce but up and down haphazardly. There are trends, upward trends and downward trends over time. So it's not truly a random sample in that way either, but maybe there's some population model. Maybe you also imagine T-bill returns and inflation rates, not just for the past 57 years or more, but for all time, as long as the United States is a country. And maybe even for many months, if you convert the monthly interest rates to yearly ones. So is that completely valid? That's up for debate. Is it reasonable? Maybe. These kinds of things I'm saying are important practical things to consider when you are trying to apply this stuff. And in particular, we are going to try to apply this to current Treasury bill and inflation environment. And I think it's probably not going to be as accurate as you might hope, because, you know, each individual year has different circumstances that led up to that year. The standard errors here are effectively estimates for standard deviations of certain sampling distributions. Say that again. Those standard errors are effectively estimates for standard deviations of certain sampling distributions. What distributions? The distributions of the slope and intercept B1 and B0 as abstract statistics, not observed values of abstract statistics. These are observed values that we got these numbers when we actually computed these in the spreadsheet. You can call those statistics too, but in this class, we've emphasized statistics are really random variables that have distributions. They are random variables that are functions of a random sample, x1 through xn, say. And maybe in this case, both x1 through xn and y1 through yn, perhaps. Well, it's a little bit more subtle than that. B1 and B0 have distributions. They are random variables, and therefore you also, when you do the reading, will see capital letter versions of them. Capital B1 instead of lowercase b1. The formula is the same. Okay, here we're going to talk about the perspective that we take. We're going to treat the x's as known and leave those lowercase x's, and treat the y's as random variables and make the y's uppercase. So the same formula in the book except keep the x's lowercase, change the y's to uppercase. The y's are now random variables. Even more subtly, they're really conditional random variables. yi is a random variable that models the variation in y values when x takes on a certain value. In fact, when x equals x sub I. This is an equation that's now defining B1, capital B1, as a random variable. Because capital Yi is a random variable, modeling the values of y when x is known to be x sub I, little x sub I. So it's really a conditional random variable. Yi given, or you might say y given x equals xi. You might even write this. You might say yi is y given xi, or you might also write that as y given capital X equals little xi, to be a little bit more precise. Capital Y is a random variable, and therefore capital B1 is a random variable, and therefore capital B0 is also a random variable. It's capital Y bar minus capital B1 times capital X bar. Same equations as before, but we're using uppercases in the way we want to think, to emphasize the way we want to think about these things. What kind of distributions do they have? Chi-square? Gamma? No, they have the most important distribution. They're normal. Why? Based on the assumptions of the model. Well, let's just write it down. Could say, what are the distributions of B1 and B0? The slope and the intercept as estimators. Using that word too, estimators. Just like X bar is an estimator from you. B1, the capital B1 is an estimator for little b1. Or, well, no, that's not right. Little b1 is an observed value of capital B1. Capital B1 is an estimator for the population slope called, oh, here come Greek letters again, called beta 1. Little b1 then would be an estimate based on a random sample, an observed value of capital B1 that would be an estimate for beta 1. This is an estimator. We might wonder, again, what is its distribution? The answer is going to be normal. What's its mean? What's its variance? The mean of B1 is going to turn out to be beta 1, which will mean capital B1 will be unbiased, an unbiased estimator for beta 1. Hey, good. We like unbiased. We make some assumptions. First thing we assume is we assume the population regression line. Well, we assume here's a better way to say it. We assume the curve of regression, mu sub y given x, from chapter 5. We did do a curve of regression example in this class, 3 weeks ago or something. It was when we were adding non-independent random variables. And we could not do a convolution. We had to do a double integral because the convolution only works for independent random variables, adding independent random variables. So we had to have the joint distribution. We had to assume we knew the joint distribution and then compute the marginal distributions by doing integrals, conditional integrals, distributions, and then doing another integral to compute a mean. It's chapter 5. And in general, in the abstract, when you do such calculations, most typically, you do not get a linear function. But here in chapter 11, we assume it's a linear function so that we can actually apply regression. We can apply the theory. The intercept is called beta 0 and the slope is called beta 1. We assume the curve of regression is linear. Is that right? Most likely not. Isn't that weird? It's not really a setting to really estimate probabilities in any usual sense, but if I was going to sort of be hand wavy, I'd say the probability that the true curve of regression is linear in any given situation with in abstract, whether it's abstract random variables or in real life, I'd say the probability that this is true is 0. So why do we use it? Well, because in mathematical and statistical modeling, even if it's not exactly true, it's hopefully good enough, right? Hopefully good enough. Is it reasonable? Does it make decent predictions or help us make decent predictions? We also assume that these yi's equal the curve of regression evaluated at xi plus some random amount called capital EI. And you could plug this in there and get that this is also written as beta 0 plus beta 1 xi plus EI. Capital EI is a random variable. What random variable? We just assume it's got a certain distribution. That's all we do. Also, assume. Don't prove, assume. This has a certain standard distribution. It's going to be normal. With what mean and what variance? Capital EI is acting like an error term, so to speak, in this equation, indicating that sometimes yi is above the mean of y for the given x, and sometimes it's below. Maybe about half the time it's above and about half the time it's below. That would be the simplest thing to assume. So we're going to assume the mean is 0. How about the variance? I guess it would depend on the situation. Just call the variance sigma squared, where sigma squared is unknown. And in fact, s squared, which is SSE over n minus 2, I showed you that 15 minutes ago, is an unbiased estimator for sigma squared. These two assumptions, well, or the second assumption, these two things here are going to imply that each yi is normal. But the mean of the yi is not going to be 0. it's going to be this mu. Or this, in terms of the betas, this thing. Beta 0 plus beta 1 xi is the mean. And the variance is going to stay sigma squared, the same as the variance of EI. There's some bad typos in your book. You might have been wondering about if you did the reading on page 387. First of all, at the top of the page, they say little b0 and little b1 vary from data set to data set, and it is evident they are actually observed values of random variables, which we did note by what? Beta 1 and beta 2? No. Bad typo. This should be capital B0 and capital B1. Didn't even get the subscripts right. Page 387. Another bad typo is further down the page in this box, which summarizes, at least in these two parts, what we already just said. The mean of the of yi is beta 0 plus b1 xi? No. B1's a statistic, not a parameter. Replace B1 with beta 1. The yi's are also independent. Why? Well, we effectively assume the EI's are independent. That's why. It's another assumption we make. We know from our past experience that independence helps calculations work out more nicely. Before next Tuesday, make sure you study these derivations. The distribution of B1 is derived. It's normal with a certain mean and a certain standard deviation of a certain variance. And the distribution of B0 is derived. Study those for next time. We will go over them to some degree, but I do want you to work at understanding them to put the theory together. In a few minutes that we have remaining, let me just show you what happened this morning with Mathematica and with R. So with Mathematica, the thing you want to use to get spreadsheet data into Mathematica is import. I need to start the kernel going here. Import, and you can look up how the syntax by clicking this information button. But you also, if you start typing quotes, it'll bring you to a file browser. File browser. So I'm looking for the spreadsheet. And where is it? There it is, treasury bill and inflation data. And it looks at the directory structure in my computer and goes to the correct thing when I choose it that way. Let's call this raw data. There it is. Oh, raw data is protected. Okay. Maybe make the data lowercase. There we go. That's the data for year, T-bill, and inflation rates. How do we work with this? How do we work with just the T-bill and inflation rates? It's a bit tricky. I had to experiment a bit. See if I remember. X data. There's 57 data points. There's actually the length of this raw data. Let's see. Okay, it's structured in such a way that to see the true length of the data set, I have to do that. And it was actually 56 though, because the first row was the labels, the year, the T-bill, and the inflation. So this is a little tricky. If I want the X data, which is going to be the T-bill data. Oh, that's the inflation data, excuse me. Let's call it inflation data. I have to do something like this, I believe. Let's see. Trying to go a bit from memory here. little weird. And I'm trying to get rid of the labels too. So I'm actually gonna go from 2 to 57. Okay, that didn't work the way I was expecting. Let's see. Maybe it's a 1 in there and an I there. No. Okay. I did it before class. I got it to work. Okay, I think. Yeah. Okay, we're almost out of time, so I better stop there. I'll figure it out before next Tuesday. Maybe I'll just figure it out. I'll send you this file for how to access the data. And then you can do the fit like I showed you last time. With R, I tried importing it through this file structure here in RStudio. And here was the file. Try to import data set. And it said preparing. Then it said install required packages. And I clicked yes, and it did something, but it didn't help. So it's trying to install some packages here to help me upload the spreadsheet. And it takes about 20 seconds here to go through it. But then I tried to upload it again and it didn't work. Same problem happened. So I'm not sure what's wrong there. Okay. I'll try to fix that by next Tuesday. Have a good day.